Hey everyone, it's me, Miss B, and in today's video we're looking at the Unit 6, Lesson 6 Cumulative Practice Problems for Illustrative Math Algebra 1. So we're starting here with a diver. So in question 1, the height of a diver above the water. So we want to make sure we're looking at like divers above the water, the things that might be important here to notice. So then we're going to look at what we're measured. And we're using that in seconds, and h is measured in meters, so time in seconds and meters. So it looks like we are just measuring height. So not the distance that the diver has actually fallen through the air, but the height they currently are above the water. So we want to select all statements that are true about this situation. So I'm gonna highlight here our function equation because this is what we're looking at. So we want to use this to figure out what is true here. So let's look at our first option. The first option here says the diver begins 5 meters above the water. And then our second option says the diver begins 3 meters above the water. So let's look at 5 and 3. In our function here, we have a 5 and we have a 3. The 5 is attached to our quadratic piece. And so this actually generally tells you how fast that object, and in this case a person, is falling towards the ground. The constant number, which just has no variable attached to it, is what's going to describe your beginning position. So in this case, they're saying the diver begins. So we're not going to begin 5 meters above the water. That describes how fast that diver is approaching the water. The diver is going to begin 3 meters above the water. Okay, so let's keep going through our options. We have options C and D, which are talking about the number of zeros. So let's talk about what a zero is after we read through these statements. So the function has 1 0 that makes sense. So has 1 0 that makes sense. And makes sense is important because we have to take into context. Or option D says the function has 2 zeros that make sense. In this case, a 0 is when the function value or the y value is going to be 0. So 1 0 means, in this case, height being equal to 0. So this diver is not starting at 0, so it can't be that. And they are going to hit the water, and in that case, they would be 0 meters above the water, and then they would dive into it, so they would be at negative, so they would end up below the water. So the only thing that's going to make sense is to actually have 1 0 in this instance, because that would be when the diver hits the water. So when the diver hits the water. So option D is not going to make sense for us because we would not have 2 zeros here. It's not like they're starting at 0, jumping up, and then falling back down. It's just the one that makes sense. So then let's look at E and F. Okay, E and F are not necessarily related, so let's just look at E. The graph that represents H starts at the origin and curves upward. Well, the height is of the diver above the water, and they're going to start higher up and then get lower and lower until they approach 0. So that graph is not necessarily going to start at the origin. They're going to start at 3 meters and then dive down into the water. So E is not going to be correct either. And if it started at the origin, that would mean we would have 2 zeros, which we don't. And then F says that the diver begins at the same height as the water level. The water level is 0. And the diver does not begin at 0, so F does not work either. Only B and C make sense for this one. That's going to bring us to question 2, which is the height of a baseball in feet. So it's modeled by the function h, and given this equation down here, and then the graph. So let's highlight our function. And we're going to underline some important things here. It is the height of a baseball. So we know that it's not how far it's fallen, but it's how far it is up in the air. And okay, so then A is asking, when does the baseball reach its maximum height? So maximum height, right? Height we have along our vertical axis. And that maximum looks to me like it's around 60, because that's right about here. And that is going to be, if I look downwards, just before 2 seconds. So we can round it because it says about when, which means around when. So we can say about 2 seconds. Now it says about how high is the maximum. That is what I marked on my vertical axis here. That's this 60, because that is how high. So we can say about, and that's in feet, so 60 feet. Okay. And then our last question is about when, so we're looking at time, does the ball hit the ground? So hitting the ground means that we would have a height of 0. And so they want to know at what time. That is going to be not at the start here, because you notice the baseball's not starting on the ground. It's starting a little bit above the ground, which makes sense. If you're pitching this baseball, you're not going to hit it right off the ground, but it is going to hit the ground right here. So that's a little less than 4 seconds. If we really want to measure it out, maybe it's, if we cut this into fourths, maybe it's 3.75. So I'm going to say about 3.75 seconds. About 3.75 seconds. And that is question 2. So we have 2 more questions on this page, and then we have a couple on the back, 5 and 6, which are a little bit longer, but we'll get to those and they won't be so bad. So let's look at question 3. Question 3 says, each expression represents an object's distance from the ground in meters as a function of time, t in seconds. So we have object A and object B. So first we want to know which one has the greatest vertical speed, and then which one was launched from the greatest height. So those are really asking you, do you know what each of these numbers in this equation represents? So first off, we have the quadratic pieces, which are both the same, -5t squared. These just represent how fast it would fall towards the ground. But then we have the linear term, meaning it has the variable to the power of 1, and these are different. And then we have our constant terms, which have no variables on them at all. So the constant terms represent the starting height. So the one with the greatest starting height, I'm going to highlight these things here. So greatest height, our starting heights are 50 and 25. And our vertical speed is represented by the 25t and the 50t. So those are the ones that we're choosing from. So that means if it's launched with the greatest vertical speed, I'm going to choose 50t. And so that's going to be object B. And then for part B, this wants to know which one's launched from the greatest height. That's my green highlighted pieces here, which means it's going to be object A. And that's what this question is asking. It's asking, essentially, can you look at an equation and using just the numbers determine information about it? That's going to bring us then down to question 4. The function f is defined by f of x is equal to 2 to the power of x, and the function g is defined by x squared plus 16. So let's highlight our two functions here. So that way we know what we're talking about. Those important pieces stand out. They want us to find the values of f and g when x is 4, 5, and 6. So I'm going to make a little table off to the side here. So let's see. I'll say that I have x, and then I'll have f of x. That's not going to be. Need to write a little smaller than that. We'll have x, f of x, and then g of x. So make a table going across like this. We want to know when x is 4, 5, and 6. Okay. So for function f, this is 2 raised to the power of x. So that means for 4, it's 2 raised to the power of 4. So 2 times 2 times 2 times 2. And if you plug that into a calculator, or you're able to just do it in your head, that should give you 16. Now, g of x is different. This one is x squared plus 16. So 4 squared plus 16. 4 squared is 16. This is going to be 16 plus 16, which gives us 32. Okay, for 5. 2 to the power of 5. It's going to be 32. And then if we have 5 squared plus 16, we're going to get 41, because 5 squared is 25, and then we add 16 to that. And let's keep going for number 6. 2 to the power of 6, that's going to be 64. And then 6 squared is 36. We're going to add 16 to that and get 52 for this one. So now part B of this says, will the values of x always be greater than the values of g? So they want to know, will these numbers always be bigger than the values of g? They're not starting out bigger. In these two cases, they are actually smaller. But once they pass it up, then yes. So we can say once f of x passes g of x, the values will always be greater. And how do we know? We know this because an exponential function will always overtake. This just means to pass up. So we kind of say that it always overtakes a quadratic function. And there we go. So we know, because we've learned that it'll always overtake, that once it does, from there on, it will always be greater. And that's question 4. So we have 2 more questions on the back of this page, and then we're done. So looking at question 5, and then we have question 6, which also kind of has us make a graph. The question 5 gives us an image and then has a table here. So Tyler is building a pen for his rabbit on the side of the garage. So you'll notice that, like, this right here, this is the garage. So it's already got a wall there, but he needs fencing to put around it. So he needs to fence in 3 sides. So I'm going to highlight our fence here. That way you can see why we only need 3 sides for this fence. Because the rabbit can't go through a wall. So he's building a pen and he needs to fence in 3 sides and he wants to use 24 feet of fencing. So they are specifically telling us that we have a width and a length. I am also going to tell you that this side on the right is also considered the width. So we have 2 widths, but 1 length. So it says the table shows some possible lengths and widths, and we want to complete each area. So in this case, we don't have to come up with lengths and widths, but the area is always going to be our length multiplied by our width. So we're going to multiply these out and fill in our table. So first off, we have 8 times 8. That is going to give us 64. We're going to have 10 times 7, which is 70. 12 times 6, which I believe is 72. Yeah, it is 72. And then 14 times 5, which is 70. And 16 times 4, which is 64. So we did complete each area. We did that one. It's on our table over here. So which length and width combination should he choose to give his rabbit the most room? So we want the largest area. And we could say that the largest area is 12 feet by 6 feet. That is this one right here. The area is going to be the largest at 72 square feet. So that is it for question number 5. That only leaves us with one more question. That's question number 6. So in question 6, Han accidentally drops his water bottle from the balcony of his apartment building. So he's dropping it accidentally. Hopefully it survives the fall. Or maybe it's just plastic and it's not going to damage. Who knows? So the equation d equals 32 minus 5t squared gives the distance from the ground in meters after t seconds. So I like to highlight, maybe not in pink, I like to highlight my equation, and then we want to know it's the distance from the ground, so that's important for us to know. And we want to complete the table and plot the data on this coordinate plane. So we are using this function and essentially just plugging these numbers in. So 32 minus 5t squared. Well, if we start by plugging in 0, 0 is often the easiest number because that means that anything with a variable becomes 0. So essentially here we have 32 minus 0, so that would start us at 32. So that's the height that he's originally dropping it from on accident, but still. Then, and you may want to use a calculator for this. I know you get a calculator to use on your test, so don't be shy. But it's always good to also check and see if you can kind of do some of this in your head first. But I'm going to use a calculator here just for time's sake. So when we plug in 0.5, you want to make sure that you are plugging this into your calculator using parentheses. But you should get 30.75. Well, now when we plug in 1 is also pretty easy, so I don't even need to use a calculator for this one because 1 squared is 1, which means that this is going to become 32 minus 5. So when we have 32 minus 5, that's going to give us 27. Now, you might use a calculator for doing that subtraction, and that's okay, but whole numbers are generally easier to work with. But the fractions and the decimals like 1.5 and 0.5, always good to check yourself on. So when we plug in 1.5, we'll have 32 minus 5 times 1.5 squared. and this is going to give us 20.75. And then plugging in 2 squared is 4. And I can do this one in my head, so I'll show you what I'm thinking. 2 squared is 4, so we're going to have 32 minus 5 times 4. 5 times 4 is 20, so 32 minus 20 is going to give me 12. So 12. Let's plot these on our graph. So at 0, we're at about 32, puts me right here. 0.5 is 30.75, so right just above. At 1, we're at 27, so right about here. 1.5 is 20.75, so right just above 20. And then at 2, it's at 12, so right about there. So we have this nice curve shape to our graph. See if I can get this to close enough, but it looks pretty. So even if I don't quite hit the that second dot there, it's still good enough. But I'm showing you the dot so you know where it lands. So now let's answer this question. Is the water bottle falling at a constant speed? And then we're going to explain how we know. So falling at a constant speed would mean that this would mean that we would have height changing by the same number. And then that would either be like adding or subtracting. And if we had that happening, this would be a linear graph. It would be a line and not a curve. So we would say, no, it is not, because the graph is not linear. So that also kind of covers explaining how we know. We can say the water bottle is speeding up. So we've answered that question, is it falling at a constant speed, and explain how we know. And if you're not sure and you don't want to use the graph as an explanation, you can always also show the difference between each of these pieces and do some subtraction here, etc. And you'll find that those numbers are different. But beyond these questions, that's really all we have for this assignment. So hopefully this video was helpful, and thank you for sticking with me through it. So this has been Unit 6, Lesson 6 of Illustrative Math, Algebra 1.